talk recorded?
Yeah, it's recorded and we're starting right now. So hi, everyone. We're here for our next session. We have Dawn Song, CEO of Oasis. She'll be doing a talk on advancements in zero knowledge proof and secure computing. And I'll let her take it from here.
Okay, great. Hi, everyone. And thanks all for being here. So today I will talk about some of the recent advancements in zero knowledge proof and secure computing in our work. So first, as everybody may be familiar with the zero knowledge proof. So, oops, hold on 1 second. Okay, so and people can see the screen, right? Okay, so so as people know about zero knowledge proof, in general, in zero knowledge proof, there's a prover and there's a verifier. And the prover has a witness W, so the prover wants to prove to the verifier that she knows W such that f of W equals to Y, but without actually showing verifier what W is here. And so, and zero knowledge proof needs to have this completeness, soundness, and zero knowledge. And in particular, the verifier in this case should now learn information about W. And there has been tremendous amount of work and progress made in zero knowledge proof protocols in general. And when we look at these protocols, there are usually a few aspects that we need to consider in terms of comparing different protocols. So first is on performance. So on the performance side, there is the prover time, how long it takes for the prover to generate the proof. And there's a verification time, how long it takes the verifier to verify the proof, and also the proof size. And also another aspect is the trust model, whether the protocol requires trusted setup or not. And so there are a number of applications for zero knowledge proof. Of course, it's a very general primitive. It can be very, very useful for, in general, again, proving the knowledge of something without actually revealing that piece of sensitive information. And in particular, in blockchain, there has been really exciting applications of zero knowledge proofs. For example, in these privacy coins, how you can essentially enable private cryptocurrencies that protects the sensitive information about the transfer of tokens. And also more recently with Ethereum's scalability challenges, zero knowledge has been used for what's called ZK rollup to help actually perform more layer 2 off-chain compute and still enable the computation results to be verified on layer 1. So, but however, today there are still a number of open challenges in the protocols that have been used in these applications. So one, for example, for many of the for some of the zero knowledge proof protocols used in applications such as in Zcash, it actually requires trusted setup, and also the prover time is slow. And also, for example, in some of the other zero knowledge proof protocols used, the proof size can be big, and also the prover time can still be slow. And so in our recent work with, we have, in particular with my students and postdocs and so on, so we have been developing new zero knowledge proof protocols to have better performance, and also in certain cases without requiring trusted setup. So, and in particular, the in the zero knowledge protocol Libra that we proposed, it's the first ZKP protocol with a linear prover time and succinct verification time and proof size. And in this one, only requires one-time trusted setup. And then as a further improvement from this, in the Merkle ZKP protocol, it removed the trusted setup and while still maintaining low prover verified time and low proof size. And this is the comparison to the different ZKP protocol. And as you can see, that in particular, so with Merkle, it doesn't require trusted setup, and from the performance, from the different aspects, it performs very well. And in particular, here in this slide, you see the concrete measurements for proving Merkle tree roots with 256 leaves. And so in this case, as you can see, in terms of the verification time, Merkle and Stark are the most efficient. Others of magnitude more efficient than other solutions. And in terms of the prover time, Merkle is the fastest, has the fastest prover time, and with orders of magnitude, is orders of magnitude faster than other approaches. And in terms of the proof size, is also is comparable to the best protocols in this aspect. Right. And so we have open source implementation for these ZKP for this new ZKP protocols, and we are looking into we are exploring how to use these protocols to help build up more efficient solutions for the different applications in the blockchain domain. And one of the things I wanted to mention is also new work that has been done with my students and former postdoc and so on. So so in this case is actually expanding the application domain for zero knowledge proofs. So in particular here, the problem setting is we have a server that has a proprietary machine learning model. In this case, it's a decision tree. And a user wants to get a prediction from the server, but the user wants to make sure that even if the server misbehaves, the user actually gets the correct prediction. And the server doesn't want to reveal all the sensitive, the proprietary information about the machine learning model. So in this case, then what we can do is that essentially the server can generate a zero knowledge proof. So the server can commit to his or her machine learning model first, and then as the user is sending a new input, the server can then do the evaluation and generate the prediction results, and also prove in zero knowledge to the user that the result is correct. It is the result of the earlier committed model, and without revealing the proprietary information such as the architecture details and without having to reveal the parameters in the model. So right, so in this work, this is the first application of zero knowledge proof to decision tree predictions, and also right, we propose a number of optimizations and new techniques to design efficient protocols for this. Okay. And this and the techniques can be general to can be generally applicable in other settings as well. So so that's the part about using some examples of recent advancements in zero knowledge. I'd like to also talk about some recent advancements in another domain, a related domain in secure computing. More other aspects in secure computing. So zero knowledge proofs again can help prove that computation is done correctly without revealing certain
Hey, Don, you need to reconnect. Hey, Don, I think you disconnected. Can you share your screen again?
Okay. Okay, can you see now?
Yep, perfect.
Okay, great. Okay, so right. Okay, so the goal of secure computing in general is to protect the computation process from leaking sensitive information. And there are actually different ways, different types of approaches for secure computing. One is by using cryptographic methods, such as secure multi-party computation, fully homomorphic encryption, and so on. And zero knowledge proof can help solve certain problems in this domain, in certain settings. But overall, for all these crypto-based methods, the challenge is that oftentimes it has significant performance overheads. So, for example, even with the improvements of the zero knowledge proof ZKP protocols that I showed earlier, it actually has orders of the performance overhead is orders of magnitude. It can be orders of magnitude higher than the original native computation. And also in general, because of this cryptographic based approaches can only be can only apply in limited specific application settings. Another type of approach for secure computing is using trusted hardware. And in this case, essentially utilizing hardware mechanisms in combination with software mechanisms can help protect the computation process from leaking sensitive information. And the advantage for this approach is that the performance can be very good. It can be close to native performance, and hence can support for general purpose computation. And so, here I also wanted to talk about some of the recent advancements in secure hardware. There's been, and so for example, my group also has been developing new solutions in this space as well. So again, let me just talk a little bit about the secure hardware side. So with secure hardware, essentially by utilizing hardware mechanisms, we can and combined with the certain software mechanisms, it can help create isolated execution environments that also often called the secure enclave. And when the program is run inside the secure enclave, the outside applications and operating system cannot observe what's running inside. and also cannot modify what's running inside the secure enclave, and hence provides the confidentiality and integrity of the execution inside the secure enclave. And also at the same time, it can help enable what's called a remote attestation, to enable a remote verifier to verify the to verify what's running inside the secure enclave and its initial state, and hence verify the correctness of the computation result. So because of the strong security capabilities of the secure enclave, it's an important cornerstone security primitive, and can enable a platform for building new security applications that couldn't be built otherwise for the same practical performance. Due to its importance, different hardware manufacturers over time have all been developing different types of secure hardware solutions. But however, there are still many challenges in secure hardware. For example, how secure can it be, and what threat models, and what would you entrust with the secure hardware? Your Bitcoin keys, your financial data, your health data. And ultimately, can we create a truly trustworthy secure enclave as a cornerstone security primitive that can be widely deployed to enable secure systems to be built on top? If we can do this, it can help usher the whole community into a new secure computation era. So what's the path to trustworthy secure enclave? I truly believe that first, it needs to have an open source design. The open source design helps provide the transparency needed to enable high assurance and help build a community. And also, we need to enable flexibility and extensibility for the design to support diverse use cases. And ideally, we should have formal verification of the secure enclave. And also, we need to ensure the security of the supply chain management for the hardware manufacturing process. So towards achieving these goals, at Berkeley, we have been building an open source secure enclave called Keystone. And in particular, it's an open source framework for customizable keys. It provides a simple, much simpler abstraction than previous solutions. For example, it decouples core security primitives from all the other features, and it utilizes the hardware mechanisms as standard from standard RISC-V features for memory isolation. And right, so it's built on top of RISC-V, which is open source RISC architecture. And with its modular and flexible design, it can enable a broad spectrum of different use cases. And with this simple abstraction and again the modular design, it has a minimum trusted computing base, which makes it much easier and better suited for formal verification as well. And right, so Keystone enables a new paradigm. So it's not just building one open source enclave, it's actually providing an open source framework for customizable keys that enables a broad spectrum of different types of keys to be easily enabled. And with our experimental results, it shows that Keystone, the framework can be very efficient. With some of the machine learning benchmark, it can be close to native computation as well. And today you can try out Keystone on the latest RISC-V chip, and also you can run it on FPGA or in emulation environments. And together with the community, we have been building a vibrant community for Keystone and more generally for secure enclaves. And the Keystone is also becoming in the process of going through the process to join the confidential computing consortium as well. So with this capability of secure computing and so on, what new applications domains can it enable? So I wanted to just talk a little bit about its application in data tokenization and global data economy. As we all know that data is a key driver of modern economy, and more data is being collected every day. And there's statistics that the global data economy is simply like at least trillions of dollars. And by combining secure computing and blockchain, we can actually move towards a more responsible data economy, where we can help tokenize data and give control to users and help create incentive to share data. And in particular, for again, with a combination of secure computing and blockchain, we can enable a new paradigm called data tokenization. In this case, the blockchain can help provide an immutable log of users' rights to data and how they want their data to be utilized. And also, with the secure computing, it can help ensure the data remains private during compute and cannot be reused without permission. And this combination of data and policy creates a capsule, which creates a new type of assets that we call data assets, that can help users to gain more value. And at Oasis Network, it has actually the Oasis Platform helps enable these new applications as well. So with the data tokenization, it can unlock a new responsible data economy where individuals can maintain data rights and earn value from their data assets. And there are some, right, so here I want to just briefly talk a little bit about some of these use cases for this data tokenization and a responsible data economy. So one application is, so people may be familiar with liquidity staking in yield farming today. So with the data assets, instead of liquidity staking, users can actually do data staking. And with the data staking, users can stake their data assets into a pool that we call data trust. And as data consumers utilize the data, they can provide payments and so on. And users can then earn reward as data yield. So this is one example use case of how users can use the data assets to gain value. And more generally, we can actually help create what we call data DAO to actually enable these decentralized autonomous data organizations. And so this can help essentially attract and incentivize data owners and can enable database collaborations. So one can imagine that users join these data DAOs to actually help create, for example, a data organization that helps with the societal, helps pulling data for societal benefits. And in this case, users could, So for example, the data in this data organization can be used by medical researchers for their medical research, but while maintaining users' data privacy. And another example use case I wanted to briefly mention, this is a use case application that actually has been launched on the Oasis platform, is in the genomic domain. So in this case, the data asset is in the domain of genomic data. And here, users have their genomic data stored in encrypted form, and they can give consent for how they want their data to be used. So for example, they can give consent to a genomic company, in this case, for example, Nebula Genomics, to do genomic analysis on their data and provide user the results. And then in this case, the genomic company can then run their genomic analysis after getting the consent inside the secure execution environment using the secure computing technology. And so in this case, the genomic company will not get a raw copy of the user's data, and so will not be able to use the data without will not be able to use the data that does not comply with the original user's consent. For example, can now just take the data out and try to sell it and use it for other purposes and so on. So, right. So this is a great example showing using this type of technology, users can become owners of their genomic data and still enable and maintain control of their genomic data, and also at the same time to utilize the data in a privacy preserving way and gain benefits from that. And so we actually have a beta launched, and actually hundreds of users have already actually joined this beta launch, and we encourage users, if they are interested, to join this as well. And another use case that I wanted to just talk about briefly is we also have a partnership with the Binance on the launch the Crypto Safe Alliance to have different crypto exchanges join forces to share threat intelligence data to identify and to try to fight crypto fraud. And again, with this type of technology, we can help protect the sensitive information while it's being utilized, and even when different participants may not trust each other. And there are many other use cases and partners that have been building on top of the Oasis platform and towards a responsible data economy. So overall, using better secure computing techniques, either through cryptographic methods with the advancements in secure multi-party computation for the homomorphic encryption or genomic proofs, or through the advancements in secure hardware, the secure computing technologies help us to enable data in general to be utilized in a privacy-preserving way and help users to maintain control of their data and help data to be shared in a more responsible and also fair way to help users to gain more fair value from their data. So together, this help us to move towards a future of responsible data. And I hope that everyone can join the community to together build a future of responsible data. Right. Yeah, thank you. Hello? Can people hear me? Okay, so I see some questions here. Will this give people the power to control data and only give consent when asked? So, right, so in general, actually, users will actually, in this case, have an app, and they can, right, so they can give consent to, right, they can give consent to say how they want their data to be utilized. And then once they give consent, for example, in this case, in the genomic data use case, then the genomic company can then run the genomic analysis in the secure execution environment. So this helps users to maintain control of their data. Does this help answer the question? Are there other questions?
Cool. So if there are any last questions, if you guys can drop in the chat, that'd be great. I see another one in the chat.
So would they be able to revoke it if we don't want Microsoft to have it? So in this case, right, Microsoft will not necessarily have the data. But in general, right, so that's the advantage of having a ledger of users' policy of how they want their data to be utilized. So yes, you can then later on revoke access. So of course, for the past computation that has already happened, you cannot revoke that, but you can revoke access for future computation. So for example, if tomorrow you don't want this genomic company to compute over your data anymore, you can then change your consent, you can revoke that. So tomorrow then, starting from this point on, then the genomic company will no longer be able to compute over your data.
All right, guys. So if we're done now, do you have any closing thoughts, Dawn? Or else we can transition to our next talk.
Yeah, thanks everyone. Again, as I mentioned, I think we are at a critical time to actually help build up this future of responsible data. And so for the website, you can just go to, I think the oasislabs.com. And so I hope that everyone can work together towards this goal of building a future of responsible data. Yeah.
Awesome. Thanks, Dawn. So we're going to transition to our next talk now, which is with
Great.
Thank you.